Here is the combined summary. This research proposes a novel self-supervised and adversarial approach to hyperspectral demosaicking and RGB reconstruction in surgical imaging. The authors leverage unpaired high-resolution surgical microscopy images for training, utilizing the physics of acquisition to recover lost spatial information. The proposed spatial gradient consistency term promotes cross-band correlation and enhances image detail, while Tikhonov regularization and total variation mitigate periodic gridding artifacts. Generative adversarial networks are explored to alleviate repetitive artifacts while preserving spatial details. The authors utilize RGB images obtained intraoperatively with neurosurgical microscopes as an alternative to high-resolution hyperspectral images, aiming to improve spatial and spectral fidelity of reconstructed hyperspectral images. A user study conducted by neurosurgical experts assesses the quality of the generated RGB visualization. The proposed algorithm employs a cycle-consistent adversarial loss, which improves details and mitigates potential artifacts in reconstructed hyperspectral images. An inverse pixel shuffle loss term eliminates periodic gridding artifacts more effectively than Tikhonov regularization, preserving local spatial details. The framework consists of bilinear interpolation, followed by a demosaicking network GDemos, using a modified Res2U-net model. A spectral recovery model GSpectral converts the RGB image back to the hyperspectral image, with a cycle consistency loss enforcing consistency. A trainable neural network model GRGB replaces traditional fixed sRGB operations, generating images similar to surgical microscopy images. The generator network combines GDemos and GRGB, while the discriminator D, trained to distinguish between real and generated RGB images, stabilizes the training procedure using the least squares loss. The proposed method for self-supervised demosaicking and RGB reconstruction involves a multi-loss function approach, combining the inverse pixel shuffle (IPS) loss, total variation (TV) loss, spatial gradient consistency (SGC) loss, and an adversarial loss. This method is evaluated on a surgical imaging dataset, achieving superior performance in both spatial and spectral accuracy compared to existing methods. The Res2U-net model is used for spatial reconstruction, and a trainable RGB conversion network enhances color fidelity. The loss function combines spatial and spectral reconstruction terms, along with a novel SGC term for spatial coherence and a color fidelity term for accurate color representation. The proposed algorithm outperforms existing methods in terms of BRISQUE score and FID score, demonstrating its effectiveness. Additionally, the method is computationally efficient, making it suitable for real-time applications. This study presents a novel GAN-based approach for medical hyperspectral image demosaicking, which utilizes readily available snapshot mosaic hyperspectral images and surgical microscopy RGB images. The performance of the hyperspectral demosaicking model has been significantly enhanced by introducing the IPS loss and the proposed cycle-consistent adversarial training based on RGB reconstructions. The RGB visualization has been refined through a simple MLP model, effectively compensating for the limited spectral resolution and range typically associated with snapshot mosaic cameras. The proposed algorithm demonstrates substantial improvements over existing self-supervised demosaicking methods, suggesting potential practical implications for real-time intraoperative surgical applications. The user study involving neurosurgical experts shows a strong preference for the proposed algorithm over existing methods. The author's work is grounded in a comprehensive review of recent studies on hyperspectral imaging, demosaicking, and RGB reconstruction, highlighting the significance of these technologies in various applications, including medical imaging, computer vision, and image processing. The research focuses on self-supervised demosaicking and RGB reconstruction from hyperspectral images, leveraging deep learning techniques to improve RGB image quality. It involves using attention networks to adapt to camera spectral sensitivity and spatial gradient consistency for unsupervised learning. The method is evaluated on several datasets, demonstrating significant improvements in image quality and reconstruction accuracy. Key contributions include novel algorithms for hyperspectral demosaicking and RGB reconstruction, as well as the use of spatial gradient consistency for unsupervised learning. The research highlights the importance of considering camera spectral sensitivity in attention networks for better performance. The findings have significant implications for applications in computer vision, medical imaging, and remote sensing. The supplementary material provides additional examples, per-band pixel differences, an ablation study, and further details on the methodology, reinforcing the effectiveness of the GAN-based approach and its connection to broader research in the field of image processing and machine learning. The research paper presents a novel approach to self-supervised demosaicking and RGB reconstruction from hyperspectral images, leveraging deep learning techniques. The proposed method employs a dual-branch neural network architecture, comprising a demosaicking branch and an RGB reconstruction branch. The demosaicking branch utilizes a spatially adaptive demosaicking algorithm, while the RGB reconstruction branch is based on a color model using one-by-one convolutions. The training process involves a combination of loss functions, including IPS loss, adversarial losses, and a spatial gradient correlation term. An ablation study was conducted to assess the importance of each loss term, revealing that both IPS loss and adversarial losses are crucial components. The efficacy of the proposed method was evaluated through experiments and a user study, indicating that it outperforms traditional demosaicking methods. The paper also presents a novel approach for image quality assessment using a web-based survey app, gathering feedback from neurosurgical experts. The findings suggest that the combination of IPS and GAN loss terms significantly improves image quality, making this approach a promising tool for enhancing surgical imaging.